Uh, so before I get started, I just wanted to say a couple of things. First, I wanted to say thank you to everyone here for inviting me here. I'm excited to be here talking to you about some recent work I've been doing around finding distributed representations of keywords, web pages, and websites. And before I get into the meat of the talk, I just want to provide a little bit of broader context about Moz and about my role there to put this in some broader context. So I work for a software company named Moz. We're a startup company here in Seattle, and we sell online marketing software to professional marketers. And my role at Moz is to develop products. I essentially act as an idea incubator to take ideas that product managers have or that I have for product features and then prototype them, and in many cases push them all the way to production. So the motivation for solving these problems that I'm going to talk about today is to develop product features. However, I try to, whenever possible, develop general purpose algorithms. And there's a couple corollaries of this. The first is that I'm motivated oftentimes by the architecture that I'm going to choose to solve these, by the product requirements that we have. Okay, so getting into the talk then. So the motivation for this talk is that we do a lot of web crawling at Moz, and we want to, Moz is one of the main products they sell is SEO software, search engine optimization software, and so we really want to understand how keywords and web pages and websites are related. And we can sort of have two assumptions. The first is that keywords can describe some type of topic or concept or entity. And the second is that we think that if we have enough of them, or a couple of them, that they can also describe a web page. And so it's natural to ask the question, can we learn representations for keywords and web pages that encode some type of semantic similarity between the two of them? And then also use for other tasks too, as we'll talk about. So the two problems that I'm going to discuss today are one that's related to web search. So this is finding some similarity measure between a keyword and a web page. And the second is that if we introduce some additional measure of authority, of how important a particular page is, then we want to ask the question, can we learn relationships between topics or keywords and websites and the authority of that topic on that site? So we could say, for instance, that this particular website, if they write about this topic, then they're an authority on that, but not something else. Okay, so some of the challenges that we're going to have to deal with in order to do this effectively. The first is that web pages have a lot of structure, and they have additional structure beyond just typical documents. They have additional metadata associated with them. They have attributes associated with the page that aren't necessarily visible on the page. And so we'll need to find some way of dealing with this. The second is that, for instance, in looking at the topic, the authority topic relationships, websites publish articles on lots of different topics. And so in order to get representation for an entire website, we're going to need to find some way of dealing with all of the different pages that it publishes and all the different topics. And then the third one is that, especially in the second case, is that we want to solve multiple tasks simultaneously. And I'll describe what I mean by that shortly. Okay, so the first main problem I'm going to talk about is this one of web page ranking. And so our goal here is to develop a product because we're a software company, but we essentially want to develop a product that will help marketers optimize their web page for a list of keywords. So the idea is that I've got a lot of keywords and maybe I want to rank in the search results for them. So I want to make my page highly relevant to this list of keywords. And we're going to do this by learning a similarity function that will compute the similarity or the relevance between a given keyword and a web page. Some of the requirements that we have for this is that we want to gracefully handle a lot of vocabulary words. There's a large variety of different long tail named entities and brand names and other things that you find on the web, and we really don't want to restrict ourselves to a prescribed vocabulary because it could get just to be too large to deal with. So we're going to use a character-based model here. And then the second thing is that we would love to be able to tell the user that this is the similarity between this keyword or this list of keywords and these different page attributes that you have. Like this is the similarity between the keyword and the title, or the keyword and the meta description, or the keyword in other parts of the page. in addition to just some overall aggregate similarity.
Would you mind just going back one slide?
Sure.
So is it correct that you're describing this as learning a function, but the function that you're learning is an approximation of another function, right? Presumably Google's. So Google has a function like this, and the function you're learning is an approximation of that. Is that right?
Sort of. So yes and no. We're going to train this via click logs. So the data set that I'm going to use to train this model will be a user types and a query. And they're presented with a list of search results, and they choose to click on one of those that they determine to be the most relevant for the query. And that's going to be the positive training pairs that we're going to use to train this. Now, the keywords, the list of options that they're presented come from Google's algorithms. So you can't necessarily decouple the two, but we're really trying to go after like user and then click. Yeah. The third requirement is that this needs to be easily interpretable. So we're actually going to try and give the model output more or less directly to the customer and let them use it directly. And so they need to be able to understand it easily for someone who is a marketer and who isn't a researcher. So as you might expect, because this is a commercially important application, there's been some previous work on this. And Microsoft Research, the group at Microsoft Research has several papers that they've published over the last couple of years that do this in various ways. And so I'm going to essentially extend their work. Now, in all of their papers, they've only considered their document as just a single web page title. So here, whenever we see document, it's just the title of the web page. It's not the full web page. But so the first paper they published was this paper in 2013, where they introduced this idea of these character-based models, and it actually works pretty well. And so I'm going to use something similar to this. So the idea with this is that your representation for a token in your keyword string or your title string or something is represented by a bag of character n-grams. So they used 3 grams, but the idea is that, so I take a token, and then I can have a dictionary then of, say, in their case, about 30,000 different 3-letter character n-grams, learn embeddings for each of these things, and then represent my token then as essentially this bag of n-grams. This is interesting because you can get the token representation by doing essentially just a single matrix multiplication. So you represent the token, this bag of n-grams, in this 30,000 dimensional space. It's a sparse representation because each token might only have, say, 10 characters or something like this. But then if you learn embeddings for each of these character n-grams, then you can get this lower dimensional, this 300-dimensional representation for your token by just doing a single matrix multiplication followed by nonlinearity. This actually works really well. There have been some recent papers, very recent papers published that extend this and get really impressive results doing things like semantic similarity with this. This group at Microsoft Research has written a couple of papers on this topic using increasingly more complicated models. This is the most recent one, which is this 2006 paper, where they, once you have a representation for your token, you need to find some way of encoding that into a representation for the entire query string or title string or something like this. And in this case, they use a recurrent neural network, a particular type of recurrent neural network called an LSTM, which stands for long short-term memory. But the idea is that this thing can essentially read the query string or the title string from left to right, and then keep track of some hidden state. Then the final output of this, the final hidden state of this LSTM at the final token will be a representation for the entire string. And so I'm going to use something like this. In this paper and all the previous ones, they trained this using click logs and negative sampling. So how these algorithms work is that they essentially take the query string, in their case the document, which is the page title, and embed them into the same space. And then you can calculate similarity using just cosine similarity and optimize the parameters by doing negative sampling. So the data comes to us in the form of positive query and positive page that the user has clicked on. From there, we can then go and do a number of negative samples where we have the query and then a bunch of pages that the user didn't click on. And then write down some loss function, in this case, the logistic loss function that's designed to separate these two things out. So we're going to try and increase the similarity of the query and positive page pair as much as we can and decrease the similarity of the query and negative page pair. This is the essential result from this paper here, and there's a lot of detail here, but I'll point out the important things here. So here what they've done is they've compared a number of different approaches for computing this query page title similarity on their data set. And the important things to point out here, so down here at the bottom is the method for their paper. They find that it outperforms all the previous methods, and in particular, it outperforms the previous ones that they had done work on. This CLSM here is some type of convolutional network for doing this. This DSSM here is some type of just a feed-forward deep neural network for doing this problem. It also, importantly, I mean, you'd expect it to outperform token-based approaches. So this ULM and the BM25 up here, these are just traditional token-based approaches for computing similarity. The other important thing is that they found that it's really important to have a task-specific representation for this. So there are lots of ways of encoding strings of text into vectors, and they compared the results to two relatively generic approaches, these so-called skip thought vectors, and then also this doc-to-vec approach. They found that they weren't competitive at all. They actually even underperformed the token-based approach. And so their conclusion from this was that you have to have a task-specific representation for this web search task, that there's something about how queries are formulated and that people actually type into a search engine, and about how web pages actually are, that you need to train a model on them. Yeah?
I guess when looking at these numbers, I wonder how significant is the gap from 38% to 43% from practical consumers?
I don't know. That's a good question. You know, this NDGC, it's you know, it seems right. Like the range in values is not very large here. So I don't know. I imagine that it is if they've actually gone through the work of trying it out. And I imagine that there's some variations of these things that are actually in production at Bing, but I don't know. Google has their own variant of this. They call this thing RankBrain. They actually haven't published any papers that I know on how they calculate it, but they have said that they train the model in basically the same way, just via click logs. Yeah.
One question for negative samples, you're choosing things that were on the first page and the search results page, and the user did not choose to click on it.
It's not clear to me from reading these papers, or maybe I have forgotten the detail of how they do their negative sampling. I don't know if they choose random samples from their training corpus, or if they actually choose ones that were on the same page that the user didn't click on. I'm not sure. Unfortunately for me, because all I get is click logs, I don't have that option. So I'm going to pick a much more naive negative sampling approach. Yeah?
Click logs, does Google sell them or something?
Google doesn't sell them, no, but there are third-party data providers that can get this via various methods. I think the main way is that you have some type of toolbar or something that the user installs in their web browser, which will track clicks. But we got them from a third-party data provider, basically.
So again, these numbers, I guess this is related to Ashis's question, makes me wonder, what if you changed from the title to the full page? Would that, you know, what would be the difference then for?
Yeah, I certainly shouldn't expect it to go up, but I don't know. No one's done that yet.
So why do they choose the title as opposed to the?
I think probably for convenience. I'll also hit on this in a second. The title is also one of the things that's most prominently displayed to the user in the UI, in the search results. But I think probably for convenience. And also from a marketing standpoint, if I put on my Moz hat for a second, then the title is one of the most important attributes of the page that a marketer will spend time optimizing. It's also one of the main signals that the search engine uses to determine relevancy. I don't know. Okay, so then we have all of this, right? So then the question is, well, all right, so these papers, they only use the page title. We want to extend it. We want to use additional attributes here. And the question is, well, can we do that? And what does that look like? And so if I think for a second here about which attributes are actually used. So if I type in this search query, artificial intelligence research centers in Washington, then I get Allen AI as the first hit here in Google. And when the user types in a search query and they need to decide which page to click on, they're typically given 3 bits of information. They're typically given the page title, the URL of the page that they're going to visit, and then this snippet down here. And this, in most cases, is the meta description of the page. And so we can confirm this, right? If we just look at the HTML for this page here, then this is the beginning of it. It's actually kind of clever. I wanted to point this out. I don't know who's responsible for this, but there's this comment here in the top that says, if you're looking at our HTML, then maybe you might want to apply working for a job here. But so here, right, so we see the page title here, and then you see this meta name equals description here, which is this snippet that the search engine will pull out. If pages don't have to provide this meta description, if they don't, then they'll try and extract some snippet from the page, or in some cases, they just substitute it with a snippet from the page. But we're going to use the meta description here. So to get an initial start on this, to try to make some progress before getting overwhelmed with additional complexity here, well, okay, so what if we represent our page then as these set of 3 attributes? We're going to have the page URL, the page title, and the meta description. And we're going to try and learn some similarity between these 3 attributes and this search query. Okay, so then the question then becomes, so how do we actually then, what do our encoders and what do our mappings look like? So this is what I came up with here. So this looks similar to the Microsoft papers, but it's different in a couple of different ways here. So the first, so if we start at the bottom working up, so if we take the search query here, artificial intelligence research centers in Washington, first thing you do is you can tokenize this thing and add some special start and end tokens, which help the LSTM. The second is that you can send it through this sparse bag of n-gram maps. So this lower box here is going to be, in this case, since we have 8 tokens, it's going to be 8 by, I have about 10,000 of these n-grams. This is going to be a very sparse representation. And then from there, we can learn these dense character embeddings and get our token representation by doing this matrix multiplication. On top of that, I'm going to stack this LSTM, and I'll use a bidirectional LSTM, which means that we have one LSTM that reads the sequence in the forward direction and takes the final vector, and then another one that reads the sequence in the reverse direction and takes the final hidden vector and then concatenates those 2 things. And that's going to be the representation for, in this case, the query. One of the themes that I'm going to come back to in this talk is sharing amongst the different parameters. In this case here, the token representation is shared for all of the different models. So we have one character embedding matrix that we learn, shared across all of the different models. I did this to reduce the complexity. I experimented with using ones that weren't shared, but it didn't help very much. And then I'm going to use element-specific LSTMs that I'm going to learn on top of this. So we're going to have a different LSTM for the URL, the title, and the meta description. And so then how do we combine all of these 2 things, or all of these things? So first is that we've got our raw input down here, and then we have these shared LSTMs that I'm going to use to encode each of these things. So we're going to learn one LSTM for or bidirectional LSTM for the URL, and then use it to encode both the URL string, just the string of the URL, and the query. And then I have a separate LSTM that I'm going to use for the title, and another one that we're going to learn for the meta description. So this LSTM is shared in both the description and the query. We use the same one. And now I need to combine these things. And this was the simplest thing that I could think of. And since we have these shared LSTMs that are essentially embedding these things in the same space, we could just compute the cosine similarity between them like this. And then we need this overall page similarity, and I just have a linear layer on top here, which is, again, very simple, and it's also very easy to interpret. So this is how we're going to get from these different page elements to these element-specific similarities in the overall similarity. There are some differences from the previous work. The first is that I'm using the shared token representation across all the page elements. And the second is that I'm using a shared LSTM for both of the encode the query and the page element. In the MSR work, for instance, they used a different LSTM for their query and for their title. I tried that. It didn't seem to help. Doubles the number of parameters, so I got rid of it. To train it here, we got a large number of actual clicks. So we have about 3.5 million query URL pairs that we got. Crawled the URLs to get the additional page attributes like the title and meta description and things. And then for each positive pair, I'm going to take one negative sample, just randomly from the data set. And this is a very naive approach and can certainly be improved, but it was super simple to implement. We have some regularization here. I added some dropout and L2 weight decay regularization here to keep this thing from overfitting. One important part about this is the structure of the loss function here. So I experimented with different loss functions. This is what I eventually decided on. Essentially, I have a different loss function for each of the page elements and for the overall similarity. So this loss function over here, for instance, this is the logistic loss between the positive sample similarity and negative sample similarity for the overall page. But then we also have these ones for the individual elements here. And this, to some extent, decouples these, but not completely. They have the shared token representation, for instance, and like this loss function over here for the overall similarity depends on the other ones, but this sort of decouples the different LSTMs, and I found that it helps training. So getting us some of the results. So one thing that this does do is that it learns word morphology. So these are nearest neighbors. If we look at the nearest neighbor to like the word beach, we get beaches, or compute, we get computing. Or the nearest neighbor to this like out of vocabulary term that's never seen before, like no with a bunch of O's, something that maybe you might actually see on the web. The nearest neighbor is actually the word no. So this is comforting that it does this.
How reliably are these good examples?
I mean, these are good examples. In most cases, it learns word morphology pretty well in the sense of it gets syntax, like plurals and things that would be essentially stemmed to the same root. There are some relationships that it doesn't get that I wish that it would. Like, for instance, it doesn't learn acronyms. And like I would hope, but it doesn't, that it could learn that AI is like the same as artificial intelligence. It doesn't get that level of detail.
Do you feel it does better than a sort of hand-built stemmer or acronym?
Yeah, I mean, I'm not sure how you would get this no relationship.
No, that's a great one. I'm just thinking there might be a whole bunch of counterexamples where it misses obvious things.
Yeah, I mean, potentially, yeah. Yeah, and I think that there's definitely room for improvement on this. I didn't say at the beginning, but everything I'm presenting today is work in progress. So there's definitely room for improvement here, yeah, for sure. So, all right, so how can I actually quantify how well this thing does? Well, it's actually pretty hard to do. The Microsoft papers, they have access to this large hand-evaluated data set. I don't have access to this. So what they evaluated their data on, they basically said, okay, so human quality raters, here's a query and page title. How relevant is this on a scale of 0 to 5? I don't have this. So I need to think of something else. This is a fine-grained ranking task in the sense that we're presenting the user with a lot of relevant pages and we're asking them to choose the one that is the most relevant. So the best that I could come up with, and I'm definitely open to ideas and I don't really feel comfortable with this, it seems like kind of a hack, but the idea is that commercial search engines are trained on these human evaluated data sets. And they also probably likely take into account this type of click URL feedback. And so to the extent that they actually do capture what's underlying in the data, then we can actually evaluate this against the search results from the search engine. This is a data set that I was actually able to collect. And so these are the results here, basically. So what I've done is I've taken 2,000 queries. You send them through Google, collect the search results that appear, and then you can calculate the similarity between the query and whatever you want, and calculate how well that correlates with the ordering on the search page. And these are mean Spearman correlations across this whole data set. Couple things, the correlations are low, right? Like 0.14, 0.13 is really low, but we're evaluating against Google's ranking model, which has like hundreds of thousands of different features with only a single one, so we can't expect it to be that high. Other interesting things here are that all of these approaches beat the token-based approaches hands down.
So why couldn't you just use held out data, right? The training data is this click URL stuff. So if
Yep.
you just held some out and then see how, to what extent are you improving?
Yep, I definitely did that. The numbers that you get out of that are like log likelihood. They're not super interpretable. I did do that, yeah. And so when I was training various model combinations and the little bit of fine tuning I did, which is not much to look for hyperparameter settings and things like this, then that's exactly how I did it. I had a validation set and then a test set that I can evaluate against, but it's not particularly meaningful, or at least it wasn't to me. I get some number, I don't really know how to interpret it.
Well, but you could get a number that's, I mean, you could compute these numbers.
I could.
Just
Yep.
relative to the
Yep.
data set.
Yep, it's good. I mean, I have some of those results. I didn't put them in here, but yeah, I could absolutely do that.
I guess the other baseline, I'm not familiar with ULM, but BM25, right, is an IR distance measure. What about using a supervised model that's not neural network based, like SVM or whatever? That would also be an informative baseline that presumably would outperform BM25 because it's using the labeled data.
Yeah, it should. I could do that. I haven't done it. Yeah, that's definitely something that I can do. It's a good idea. So quickly here, because I want to move on to the next section of the talk, but basically this Plangital, this is this Microsoft paper that uses this LSTM. So this is my implementation of their model. This is a bit different from theirs in that I'm using a shared LSTM. But anyway, it at least allowed me to examine my results against a similar thing here. And what I found is that in most cases I'm outperforming theirs, which is comforting. This URL one is actually interesting here. So the correlation is lower on the URL string. I'm not sure exactly why that is. I need to think a little bit more carefully about that. But I think it might have something to do with the fact that I'm using this shared token representation for all of the different attributes, and things that appear in the URL string look very different than what things appear in queries and in other text. But that's that. So we have a demo of this that I put up internally. We're using this to iterate. So the idea is we want to launch a product feature. And so this demo here, the idea is that, well, okay, let's imagine that I'm a writer and I write for the Seattle Times. And I'm going to maybe write an article about AI research centers. And someone, maybe a marketer or someone told me that I want you to optimize your page to rank for this keyword. So if someone types it in, then we can drive some search traffic to our site. And so here what this is it allows you to put in this page, the page that you're creating, which is this thing over here, and I just made something up. And then you put in your keyword or a list of keywords. Then it goes out and collects the data from Google, what's already ranking on the page, and calculates all of these similarities so that you can see, okay, well, if I have this page title, Seattle Research Center is leading the way in artificial intelligence advances, then, okay, well, I am more similar than all of the pages that are currently ranking for this keyword. So that's the product use case that we're going after. We can also use this for keyword clustering, and this thing's actually in production here. So because we're using a shared encoder, we can actually use it to induce similarity between keywords. So the idea is you just take your two keywords and you send them through the query encoder, and you can use that to calculate similarity. And then you can use that to do some keyword clustering here. This was just a sort of convenient thing that we were able to get out of this. But for instance, this is one of our products. You can go and put a keyword like artificial intelligence. You can get 1,000 different keywords, and then the idea is you want to group them into ones that are related. And so, like, for instance, this artificial intelligence robot group here, you can see that I grouped together things like artificial intelligence chat robot or artificially intelligent robots or something like this. Yeah.
You assume that the company that's coming to you has a fixed list of keywords and they want to tune their page for that list. What if their keywords aren't very good, like they don't match what their product really is? Is there any mechanism to tell them, instead of tuning your page, you should come up with a different list of keywords?
Yeah, there's this whole other subset of SEO that revolves around doing keyword research. And the whole idea with this is that what are the keywords that I should target? And there's lots of things that go into making that determination. But for the purposes of this, I'm just going to assume that someone's already done that, figured out why they want to target these keywords, assume that they've made an informed decision. That's a separate problem that I was trying to solve. But yeah, that's definitely an important point, right? Like maybe, like this keyword is probably actually not a very good keyword at all to target because probably almost no one types this in. You probably want to target something that has more search volume or something like this if you actually want to drive traffic to your site. But it was an example.
It feels a little bit like I'm being tricked as a user because someone writes an article about AI and you could analyze that article to see what the keywords are in it, and that would be helpful to me. But to change the article artificially kind of to target certain keywords is trying to like trick me to go to that page. See what I'm saying?
I mean, that's I mean, yeah, no, certainly. And I mean, so SEOs have gotten a bad reputation precisely because of activities like this. In this case, I mean, you can potentially make the argument that, and this is getting a little bit far afield, but you could potentially make the argument that, well, like I'm actually improving the user experience by making my page, like making my title actually be something that's understandable to a user that has the intent to go to my page. Doing things like manipulating the link graph and like building link spam and things like this so that links are a ranking factor. They're a very important one to drive my page up artificially in the search results. So yeah, I'm not making any statements about whether this is an appropriate activity to do or not, only that for the company that I work for their customers, this is an important activity.
I guess you could argue if you started with a pre-written article and now your goal is, it's sort of just like advertising, right? Like
Yeah.
people seem to buy my toothpaste more if I put it in a red box. I'll put it in a red box. It's not, it's still tricking your, optical sensors to respond to something, but it's not necessarily devious.
Yeah.
You're training on click-through data here, you said, is that right?
Yes.
So the assumption is if Google shows it in the top 10, then the user will click on it. Is that what you're...
The assumption is that if the user types in the keyword and they decide to click on the page, then they found that that search result met their intent. That they were presented with, so you type in a query, you're presented with a list. As a user, I can choose which one I want to click on. Then I'm going to choose to click on this one because the information that's presented to me in the search results in the user interface suggested to me that that was going to most satisfy my intent.
So this doesn't do anything about making sure it's in that list in the first place?
No. Okay, so some next steps here to wrap up this section. So the obvious next step is that we can extend this to the full page content. I haven't done this yet. I have a bunch of ideas about how one might do that. I'd be happy to discuss them in the Q&A or offline or something. The second is that one of the things that I hinted at is that this token representation, I wish that it were better. We could potentially improve it. There's this great paper by Kim et al. Talking about character-aware neural language models that actually stack some additional layers on top of some highway layers in there that they find is helpful. Third thing is that I wonder if using this LSTM is really necessary. I always try and bias on the level of simplicity, and I think you could potentially simplify it. And then I've done relatively little fine-tuning on this. My negative sampling strategy is really simple. Could definitely get some gains there. I haven't really done any careful hyperparameter exploration. This was really to get a prototype out and to push it back to the product team and let them figure out how they're going to figure out the workflow. Okay, so I want to switch gears now, talk about this keyword site authority thing, calling this thing topic reach. And for a moment, reasons that become clear in a second. So this is also work in progress. So this is our motivation for doing this. So one of our products, we have a web crawler that crawls news sites and blogs and things like that and indexes them. And so this is one of the pages on TechCrunch that it crawled about car sharing in Portland. And we get a couple of interesting informations with this that we add. The first is that we get this thing called this reach. This is some measure of the importance of the page. It's basically a weighted average of social shares and links and things like that. It's not really important to understand exactly how this thing works for the purposes, but you can imagine that for this product's customers, this is something that tells them how much impact this page had with their audience. The second thing is that we get this list of extracted topics. And these are keywords that get extracted from the page via some machine learning pipeline. This is a project that I worked on last year and put this together. I can go into the details of this later, but basically this is two-step process. We have this NLP pipeline that will analyze a web page, pull out a list of potential candidates, and then we have this ranking model that will say these are the ones that are the most relevant to it. So it does keyword extraction. In this part of the talk, I'm going to switch to calling these things topics because I think of them really as topics, but they're basically keyword strings. So for instance, you can see here that it pulls out words like reach now or BMW car sharing or things like this. So on TechCrunch, they publish lots of articles on lots of different topics, and they all have different amounts of importance or different reach. And the motivation is that we'd really like to understand how these things are related. So if I'm TechCrunch, what are the things that I can write about that are going to resonate the most with my customers? Or if I'm one of TechCrunch's competitors, then what are the things that they write about most that resonate with their competitors, and how can I use that to inform my content creation strategy? That's the motivation. So there's some issues that we're going to need to deal with in this one. The first is that these topics are sparse in the sense that we're going to represent each page with a bag of 5 topics. And there also has a really wide variety of different rephrasing. So we're going to need to find some way of dealing with this. The second is that there's a really wide range of these reach scores across different sites. Like if TechCrunch writes an article about car sharing, then a bunch of people might share it and link to it. If I write an article about car sharing on my site, no one ever looks at my site, then it could be the exact same article, but no one's going to actually look at it. So we need to find some way of dealing with this across sites. And the third is that sites publish articles on many different topics. And so if we want to learn a representation for an entire site, then we need to be able to somehow aggregate up all of the different pages that they've published. Okay, so a little bit more formally then, the goals for this is that I have these 3 tasks that we're going to train this multitask network to do simultaneously. The first, so we want to learn representations for topics and sites in a way that gives us these 3 things out. The first is that we want some function that I can take a site and a topic, and it'll tell me the expected reach of that if that site were to publish an article on that topic. The second is that I want to recover a generic topic-topic similarity. And the third is that I want to recover some type of semantic similarity between sites and topics. And so this is different than the reach one in that, like, TechCrunch might publish a lot of articles on like iPhone apps or something. But the topic iPhone apps might be highly semantically relevant to TechCrunch. But if their audience doesn't care about it, if they don't engage with it, then they're going to have a lower predicted reach. Maybe they might publish like 3 articles on AI or something, and people love it, and then they can have a low semantic similarity to AI, but they have a high expected reach. I should say that this is a general purpose algorithm, and they're actually direct analogs to Semantic Scholar. So really all that you need to do to make this work is you need some measure of importance. So in the Semantic Scholar analogy, this could be things like citations or influential citations or something. The second is that you need some, like the analogy in Semantic Scholar would be like a web page would be, the analogy would be a paper that someone would write. And the third is that the website analogy would be any entity in the Semantic Scholar world that publishes multiple papers. So this could be an author or a journal or a conference or anything like this. So you could say, for instance, that like this author is an authority on this topic, or this author is semantically relevant to this topic. Maybe they publish a lot of things on it, or this conference publishes a lot on these topics or something like this. Okay, so the idea that I'm going to explore here is that we're going to essentially embed sites and topics into the same space, and we're going to train a network that'll solve all these tasks simultaneously. And we're going to have 3 different loss functions that are all going to be jointly optimized. So we need to figure out how we're going to actually do these embeddings. For the topic embedding, I'm going to use something similar to what I used for the LSTM. Again, we're going to use a character-based approach, slightly different, although it's actually a lot simpler. I'm going to borrow this idea from this Charagram paper that was published very recently. And this is actually even simpler than the previous approach, where you literally take your entire string, doesn't matter how long it is, and take bags of n-grams and represent it as a sparse, bags of character n-grams, represented as a sparse matrix, and then learn your embedding by just doing a single matrix multiplication. I actually inserted this layer, normalization layer, in here before the nonlinearity. This helps in dealing with character strings that are of wildly different lengths. Like if I want to compute an embedding for like a character string that's 3 characters versus 20 characters or something like this, this normalization helps. For site embeddings, I'm just going to learn a representation for each site. So this is like introducing a representation for word2vec or something, or for tokens. Just each site is going to get its own vector, and we're going to learn what this is. Okay, so the reach predictor, and I think this is actually the challenging part about this. And this is the one that I've iterated the most on. I have a long list of things that I tried that didn't work. I'd be happy to talk about what those were and why they didn't work. But this one that seems to work the best is this so-called neural tensor. And it has a form like this. It's basically essentially a linear combination of these things with this interaction term in here. So this is what it looks like. So this term on the left, so here S is, if I want, this function h of s of t is going to be the thing that's going to calculate the expected reach for a given site and a topic. And here we've already taken the site and the topic to their embeddings. So these are these 300-dimensional representations. So the first is this like S transpose WT term. This tries to capture interactions between the two of them. The second, this is a linear term here. These 2 linear terms, this VSS and this VTT, these essentially capture the overall averages. So TechCrunch, doesn't matter what they publish, it's going to have a certain reach. You can capture that via this second term, or some topics are going to resonate well with people just more than others. and that's this third term, and then there's some bias. I'm going to train this with a large dump of data from our index. So the data comes to me in this form. We have about 4.5 million different pages that we've crawled and indexed. And associated with each page, we have the site, the domain name that we're going to learn the embedding for. We have this list of 5 different topics that we've extracted, and we have the reach score associated with it. Each site has many, many pages. And then we're going to optimize this loss function. So the loss function is a weighted average of these 3 task-specific loss functions. We have a loss function that's going to be designed to make similar topics have similarity. We have another loss function, which is the site topic one, which is designed to semantically learn that this site has a same semantic similarity to this topic. And then we have this third one, which is the predicted reach. To do the first 2, we're going to do these things via negative sampling and co-occurrence. So this, the topic loss is, and we're here, in this, we're going to use this max margin loss. So it's basically the same as the logistic loss. But basically, we have a page, and it has 5 topics. And we can use co-occurrence of topics on the page to learn which topics are similar. So we have these 5 topics. We can take all of the pairwise co-occurring topics, and then we can negatively sample one, and we can calculate the similarity between these 2. For the site topic one, we're going to do something similar, except we're going to do topics that co-occur on the site. So we have a page on TechCrunch, and we have the 5 topics that it published. We can calculate the similarity between those, and then we can negatively sample a topic that didn't occur on that page or on TechCrunch, and use that to learn the site topic semantic similarity. Then for reach, we're just going to do mean squared error. So we have the page, we have the 5 topics that appear on it. We can calculate the predicted reach, and then we can actually look and see what it was for that page, and then we can optimize the mean squared error. The negative sampling strategy, again, I implemented something super simple. This can definitely be improved, but this was a start. Training requires negatively sampling topics, but we don't have a prescribed dictionary of these. So instead, what I do is, when I'm training the model, we're using some type of stochastic gradient descent with mini batches of pages. And if I look at a page in the mini batch, I can look at all of the other topics that appear on all of the other pages in that mini batch, and I can use those for negative sampling. Okay, so some actual results from this. What if you train this thing, and what do you actually get here? So it does really well at capturing topic-topic similarity. Like, for instance, if I give it the topic Trump is the seed token, and these are the nearest neighbors. So it easily learns that Trump and Donald Trump are the same thing, and various things associated with Trump's campaign. But it actually, really interestingly, gets things like GOP debate is a really highly relevant topic to Trump. Actually, and you might think, oh, well, okay, it's going to be easy for it to get Trump and Donald Trump because we're using bag of n-grams representations. But Trump and GOP debate have almost no overlap in terms of the bag of character n-gram representation. Jeb Bush, Hillary Clinton, other politicians that you would expect would be really highly associated with Trump. Does a really good job at this. We can take a longer tail token like Node.js, which doesn't appear very frequently at all in the data set. And again, it does pretty well here. It learns that Node.js is similar to things like, well, Node, of course, you might expect, but things like GitHub or jQuery, web applications, and things like this. We can do the same thing for site. So we have this site topic similarity. So we can give it a seed token like Trump and say, what are the sites that are the most semantically relevant to Trump? And here we go. We can get basically a bunch of news sites that talk about politics or other conservative sites. We can do the same thing for, yeah, go ahead.
The results for Trump seem very time sensitive. Like before he started running for president, would it show things about his business instead of this? Like there's no history of his life.
Yeah, and that's probably because all of the data that we took is we've essentially collected, most of it's weighted for the last 6 months or something like this. This is a product that was just launched a year ago, and they scaled up their crawling and indexing probably over the last 6 months. So most of this data was collected in the last 6 months. Yeah. So Node.js, right? Another long tail query. Again, we do a good job where it's related to like Stack Overflow or dzone, which I didn't even know about this website until I looked at this result, some developer website. So we're doing a good job at this. We can actually turn it around, and we can say, all right, well, what if I give it a seed site? What are the topics that are the most similar to this site? So if I give it the site politico.com, which is a politics site, then you get topics like GOP debate and Clinton and Bill Clinton and things like this. So it does, in my estimation, quite a good job of capturing this site topic semantic similarity. The reach prediction is a lot harder. And this is actually really noisy data here. So here what I've done is I've taken all the topics that occur on the site politico.com in our data set and calculated some statistics of those. So if we just look at this top line, for instance, this min count greater than or equal to 1, this includes all the topics that occur on Politico, whether they occur once or 100 times. And we've got a large number of these things, like 9,500 of these. And here, this RMSE, this is the root mean squared error prediction of the reach. And you can see that it's actually only slightly less than the standard deviation. It actually is less than a standard deviation, which is good. But one of the things is the data is actually really noisy. And this is hard because there is a lot of topics that only appear once or twice that might be super not very relevant to Politico, or maybe errors that this topic extraction algorithm has made or something like this. And then another way of evaluating this is calculating the Spearman correlation. Like for instance, maybe I don't care about whether the model can accurately get the reach score right. Maybe I only care about whether it can rank them properly. And it sort of does an okay job. It's not great. But if we start going and thresholding this and saying, all right, we're going to throw out all of the topics that only appear once or twice or something like this, and we increase this minimum count. So we're looking at topics that appear in Politico a lot. So they're ones that are more semantically similar to Politico. We see a couple of things. The first is that the standard deviation goes down. The error also goes way down too. And the correlations go up. So the topics that are more relevant to the site, we do a better job predicting their reach. One interesting thing is that this reach prediction is not robust at all to dissimilar topics. Like for instance, if I say, what is the expected reach between Politico and social media marketing and Politico and Clinton, we'd expect Clinton to be much higher, but it's not. There's an explanation for this, partly due to the functional form that I've chosen here. Like if S and T, if the site and the topic are very dissimilar, if we expect this interaction term to kind of look like a dot product, if W is the identity matrix, for instance, then this is going to be a small term. And if we look at a particular site like Politico, then this middle term is going to be constant. So we're essentially just left with this right-hand term, which is going to try and pull out which topics are the most important all across our corpus. The other explanation for this is that during training, we only ever expose the algorithm to topics that actually appear on the site. Like we never say, hey, Politico, or hey, model, try to learn the relationship between Politico and social media marketing in a way that you can predict the reach for it. So this is somehow out of the domain or out of the data that we actually expose it to.
You have the negative sampling for, I guess, the topic, but you don't have it. So you don't have, I guess you could sort of inject zeros or something.
I had thought about doing that, yeah. I haven't done it, I haven't tried it yet. It is, when I've looked at this, it's one of the things that I've thought about a way to combat it, is that exact idea, yeah. I think it might work, but I haven't done it yet. So interesting things you can get then, right? So if we look at like Politico, for instance, right?
About 4 minutes.
All right, so I got 2 more slides. So interesting things that we can do here, right? So if we look at Politico, we look at all the topics that appear on more than 10 pages on it, we can say, okay, what is the highest predicted reach? and we can get something like this. So we can get some insight. This is interesting too because we get some type of smoothness property. Like the topics that appear are related. Like Bernie Sanders, 2016, Sanders, Bernie. These are all basically the same thing. And because we have this, basically we get, if Politico is a high expected authority with Bernie Sanders, then we should expect that it has a high expected authority with like Senator Bernie Sanders. The second thing that we can get is, this is actually one of the motivating product features we had, was that we can calculate this for all topics, not just ones that appear on the site. So for instance, we can take the site Politico and we can look at what are all the topics that are very highly semantically relevant to Politico. And then we can rank those by the expected reach, and we can look at ones that Politico hasn't actually published on. So this would be a recommendation and say that Politico, if you publish something on these topics, these are relevant to things that you already talk about. You haven't talked about them directly, but based on what your audience is already engaged with, and the fact that these are similar to things you already talk about, this would be a good idea for content for you to go out and target. Okay, so conclusions are basically, I don't want to repeat what I just said. We can learn these interesting representations of keywords, websites, and topics to do interesting things. And I just want to leave you with one final thought here, is that I wonder if you can actually combine these two approaches. So this topic reach thing, it uses this bag of 5 topics that we get from this other handcrafted, hand-engineered machine learning pipeline. Well, we have this other method of learning these nice page distributed representations by doing keyword page click logs or something like this. And so it's an interesting thought. I haven't tried this. So I wonder if we can actually combine these two and remove this handcrafted pipeline altogether and just learn representations for the pages directly. So that's it.